Say what?
Gotta do it again.
Have to do it again, so it's never recorded.
Sir Rattigan! Sir Rat is in the recording. I know not if Rats you speak. Plan for today. No, I'm not going to teach all of class like that. A, I couldn't make myself clear. B, my voice will die 5 minutes. Plan for today is we're going to finish off Standard 8 by talking about what does it mean to form a basis for a vector space today. I've got my usual office hours today and Wednesday at 11 and 1, tomorrow at 1. Also, the plan is we're going to have a Standard 8 quiz on Wednesday. And keep in mind, Standard 8 problems have been posted. I encourage you to check them out, especially after today's class. Any questions or comments before we get started for today? So, a group of mathematicians and a group of engineers are traveling by train to go to a conference one day. All of the engineers buy a ticket for the train, but only one of the mathematicians buys a ticket. Of course, the engineers are ridiculing the mathematicians for this, saying they're going to get into a lot of trouble, when suddenly one of the mathematicians yells, "Hey, the conductor's coming!" All of the mathematicians quickly disappear into a single restroom. The conductor checks the engineer tickets, goes up to the restroom door, knocks on it, says, "Ticket, please." The mathematicians slide their one ticket out, conductor goes away, mathematicians come out. Engineers are very impressed by this. So after the conference, the engineers and mathematicians are going back by train again. Engineers decide they are just as smart as mathematicians, so the engineers buy just one ticket this time between them. Mathematicians don't get any ticket. Engineers are starting to question the mathematicians, what they're thinking, when all of a sudden one of the mathematicians yells, "Hey, the conductor's coming!" Engineers quickly all rush to the restroom and pile inside. Then one of the mathematicians knocks on the restroom door and says, "Ticket, please." And with that, let's get back to talking about vector spaces. So last week we focused Wednesday and Friday on looking at what's called a vector space, which we said was sort of a generalization of Rn, and that it's a set of mathematical objects that you can add and do scalar multiplication on that has some nice properties. That contains a zero element, meaning something in your set that doing addition by that zero element does nothing. You want your set to be closed under addition. You add any two things in V, you get back something in V. You want it to be closed under scalar multiplication. You multiply anything in V by any real scalar, you get back something in V. And last week we kind of looked at several different examples of several types of vector spaces, as well as subspaces, smaller vector spaces living inside of bigger ones, like complex numbers, R infinity, all mathematical infinite sequences of reals, all n by m matrices, functions from R to R, polynomials of degree less than or equal to n, continuous functions from R to R, differentiable functions from R to R. We said that all of these form examples of these vector spaces. Oh, and I guess I should also mention there were 7 other conditions that I'm not going to write on the board because who has the time or space. But we're basically saying things like addition in your vector space is commutative, it's associative, satisfies the distributive properties, etc., etc. Basically nice properties that says it behaves like addition and scalar multiplication does in Rn. And what I want to focus on today is looking for bases of arbitrary vector spaces. So, refresher. Can anybody remind me, what did it mean to form a basis in Rn? It's something we looked at quite extensively the last couple of standards. Oh, gosh.
It's a set of linearly independent vectors which spans the
Rn?
Rn, yeah.
Yeah, so we said that a basis for Rn back in standard 7 was that you have a set of vectors that spans, say, Rn, or a subspace of Rn, in the case of looking at the image or the kernel of a linear transformation. We said that basis is just a set of vectors that spans your subspace, meaning everything in your subspace can be written as a linear combination of those vectors, and it's linearly independent, meaning there's no redundant vectors. There's no way to take any one of your vectors and write it as a linear combination of the others. Turns out the same is going to be true for an arbitrary vector space. We can since we have in a vector space definitions of things like addition and scalar multiplication. In other words, since in an arbitrary vector space we can still take linear combinations, that's going to allow us to define a basis for a vector space in an analogous sort of way, where we're going to say that given some elements, let's say V1, or not V1, A1 through AN in a vector space V, we're going to say that these elements span our vector space V if every element in your vector space can be written as a linear combination of the A sub I, meaning if there exist scalar values C1 through Cn in the real numbers, such that your element V in your vector space, your vector V, can be written as C1 A1 plus C2 A2 plus Cn times An. So in other words, a spanning set for your vector space is going to work the same way that it did back for subspaces of Rn. The only difference is that the elements of a spanning set don't have to necessarily be the usual vectors in Rn that we're looking at. But it's just a set of objects coming from your vector space that if you take linear combinations of all of those objects can give you anything in the vector space. And similarly, we could say these elements are linearly independent if none of them can be written as a linear combination of the others. If no AI can be written as a linear combination of the others. So let's do an example. Let's take a look at the complex numbers. And let's say we have a set of vectors in the complex numbers, a set of objects in this vector space, which is going to be, A1 is just going to be 1, A2 is going to be 2i, and A3, let's say, is 3 plus 7i. And what I want to know is, does this set collection of 3 elements, does that span the complex numbers, and or is the set linearly independent? So let's start with span. Would it be the case that given any complex number of the form a plus bi, can I find some linear combination of these 3 elements that'll give me an arbitrary complex number, a plus bi? Riley?
Yes.
Cool. So if I were to give you, for instance, 6 plus 5i, can you give me a linear can you write that as a linear combination of a1 through a3?
You do 6 A1 and then 2.5 A2.
6 times a1 plus 2.5 a2. What about a3?
A3 is not linearly independent.
Well, we're not looking at that yet. We're just looking at spanning for now.
It would be 0 A3.
Yeah, you could put it as 0 a3. Or if you want, you could do something like have a copy of A3 in there, a negative A2, and then a 3A1. But also be another way to get that. So Wynn, how about in general? Sorry, by the way, Wynn, before you came in, you noticed that the broom over there was missing, and I said it was probably you had stolen it.
That's fair.
No offense, I just figured if anyone was most likely to take it, it would be you.
That's fair.
Practice those domestic arts for me then.
Yeah.
Sorry, I was writing something down. What did you say?
I said he's practicing his domestic arts.
Oh gosh. So Wynn, what if we had an arbitrary A plus BI? Could you write that as a linear combination of A1, A2, and A3?
Yeah.
Groovy. What are our coefficients? Or at least one way to come up with scalar coefficients that'll give us a linear combination of A plus BI?
Well, you can just do. I'm sorry, I guess I'm a little confused by the question.
So, sorry, yeah. So Riley did kind of a specific example. If she found some coefficients that you could tack on to this A1, A2, and A3, that would make it so you could find a linear combination of those to get 6 plus 5i. And I'm asking, can you do the same with an arbitrary element in the vector space? An arbitrary A plus BI. So in other words, can you find some coefficients, and likely these are going to be some expressions in terms of A and or B, that you could plug in there?
Yeah, I mean, like A times A1, and then 1/2 B times A2, and then you can do 0 times A3.
Yeah, I think that should totally work. Because if you were to take A times A1, that would give you A times 1. If you were to take B over 2 times A2, that would give you B over 2 times 2i, and then plus 0 times 3 plus 7i. You simplified that out, that would give you something of the form A plus BI, no matter what your A was and no matter what your B is. So in other words, what Wynn just showed is that given any element A plus BI in our vector space, in this case in the complex numbers, you can write A plus BI as a linear combination of these three elements. So what does that tell us about A1, A2, and A3? Alma?
They span the complex numbers.
Yeah, they span the complex numbers. So in other words, we can say that since any element A plus BI in the complex numbers can be written as a linear combination of A1, A2, and A3. A1, A2, and A3 will span this vector space of all complex numbers. If there was some complex number that we couldn't write as a linear combination of A1, A2, and A3, then we would say it's not a spanning set. Like if A1 was 1, A2 is 2, and A3 was 0, for instance, we would say that set does not span the complex numbers because there's no linear combination of those that would give you I, for instance. Questions or comments? So This is going to give us a spanning set. Is this do A1, A2, and A3 give us a linearly independent set? Or is there going to be a way then for us to write one of those three vectors, A1, A2, or A3, as a linear combination of the others?
I mean, yeah, we can write A3 as a linear combination of A1 and A2.
Okay. Gimme. I'm sorry, we're Hillsdale, polite discourse. Could you please give me a linear combination of A1 and A2 that would give me A3?
3A1 plus 3.5 A2.
Be with your decimals. Yeah. We could say that A3 is equal to 3 1 plus 7 halves A2, which is the same as saying 3 plus 7i is equal to 3 times 1 plus 7 halves times 2i. So what does that tell us about A3? Yeah, that's going to tell us that A3 is a redundant vector from these three vectors. A1 is, for similar reasons to like what we were talking about in the previous standard, first vector is never redundant unless it's the 0 vector. 1 is not 0, so it's not. 2i is not redundant because it's not a scalar multiple of A1, not A sub I. A2 is not a scalar multiple of A1. Keeping in mind our scalars are real numbers. There's no real number you can multiply by 1 to give us 2i. So A2 is not redundant. A3, however, is redundant because it can be written as a linear combination of the elements that come before it. So we're going to say that A3 is redundant. And if our collection of vectors has a redundant vector in it, what does that tell us about the collection of the vectors as a whole? Catherine?
It's not linear.
Yeah, it's a linearly dependent collection of vectors. Which tells us that set A1, A2, A3 is linearly dependent. If it didn't have any redundant vectors in it, it would be linearly independent. Yes?
Are imaginary numbers never considered as, are they never able to be considered as scalars?
Ooh, good question. So, yes, but in this class, no, is the short answer. So technically, when we define a vector space, when you say you can do scalar multiplication, technically you should be defining what your scalars are that you're allowed to use for scalar multiplication. And so what we've been doing so far is we've been saying, oh, we're going to treat the real numbers as being the scalars you're allowed to use. So technically, what we would be calling are vector spaces, meaning vector spaces whose scalars come from the set of real numbers. If you wanted to, you could be sneaky about it and talk about C-vector spaces, or a complex vector space, which is exactly the same idea, except you allow your scalars to be complex numbers instead of real numbers. And in that case, most of the same properties will still hold, but you would have different things happen. Like if we were looking at a complex vector space where our scalars could be any complex numbers, A2 would suddenly become redundant because you could say, oh, that's just 2i times A1. But if you're only allowing your scalars to be real numbers, then A2 is not a redundant vector in this set. But that's a good question. And there are a lot of times, especially in more higher level mathematics, where you want to be careful to distinguish between the two. For instance, I will tell you that as part of my research in graduate school for my dissertation, these are the sort of vector spaces I was primarily looking at. vector spaces where you could have complex number scalars. And the reason why is long and complicated, but involves roots of unity. Yes, Ashley.
So will the general formula always be like for coefficients b over 2? Or is it just in this example where we have a2 equals 2i?
So this is specific to this collection of vectors. Yeah, if I gave you a different set of 3 vectors, I could still give you a set of 3 vectors where the third vector is redundant, but it might very well be a different linear combination. So for instance, if I'd given you b1 equals 1, b2 equals 6i, b3 equals 2 plus 2i, then you would say among these, b3 would be redundant because it could be written as 2b1 plus 1/3 b2. So it all kind of, and so b3 would be redundant in this set. But it all kind of comes down to the individual vectors. How can you write one of them as a linear combination of the others?
Gotcha.
And what these coefficients are, you kind of have to determine on a case-by-case basis.
Okay.
Good question. So this gives us, so our definitions for spanning and linear independence are really the same as they were back in standard 7, standard 6 and 7, standard 5, 6, and 7. We've been talking about these for a while now. The only difference is when you're taking linear combinations of vectors, our vectors might not necessarily be the coordinate n-tuples in Rn that you're used to. What the vectors are depends on what vector space you're working over. You could probably guess, but by the way, do you remember back in standard, I think it was the end of standard 6 where we had a theorem that said a set of vectors forms a basis for your subspace if and only if everything in your subspace can be uniquely written as a linear combination of vectors? I've seen a lot of blank faces, but I remember talking about that, so I know I'm in the right. Here's an example of 6 plus 5i can be written as a linear combination of a1, a2, and a3 in 2 different ways. Turns out that theorem still holds true for an arbitrary vector space. So the fact that we could write 6 plus 5i as a linear combination of a1, a2, and a3 in 2 different ways is going to tell me, or is going to tell us very similarly right away that a1, a2, and a3 cannot form a basis. Spoiler alert, pretty much all of our results that we've looked at for linear independence and spanning sets for all vectors in Rn are still going to work for vectors in an arbitrary vector space. And the main reason being is these 7 other conditions that say, oh, linear combinations of vectors in V works very, very similarly to linear combinations of vectors in Rn. So basis is defined the same way. It's just a linearly independent spanning set. So we can say that a basis for V is a linearly independent set of elements that span V. So just like with basis of a subspace in Rn, we need linear independence and spanning. And similarly, we can say that the dimension of a vector space V is the number of basis elements in any basis of V. Remember how we said last standard that for a subspace of Rn, any 2 bases are always going to contain the same number of vectors? Turns out that's true for an arbitrary vector space as well as for subspaces of Rn specifically. That result is generalizable to say that for any vector space any basis will always contain the same number of elements, which allows us to then define the dimension to just be what that number of elements is. So let's do an example before I set you loose to looking at some practice problems on your own. What would be an example of a basis for the complex numbers? In other words, a set of vectors from the complex numbers, or elements of the complex numbers that are linearly independent and that together will span all complex numbers. Eleanor?
1 and 2 plus I.
You're gonna make it difficult on me.
Yes.
I'm gonna turn it back on you by writing I plus 2 just to be spiteful. That would technically work. First of all, is this a linearly independent set? Well, 1's not redundant. Is I plus 2 a scalar multiple of 1? No.
As long as we're saying that complex numbers are not scalars, then no, it's not a scalar.
Yeah, so I'm going to cross this out so you all don't get any ideas. If we're looking at this as a real vector space, complex numbers is a real vector space, then yeah, I would say this is not redundant, this is not redundant, so this would be a linearly independent set. This would be linearly independent. Does it span? Given any complex number, can I write it as a linear combination of 1 and I plus 2? John, what do you think?
Yes, but I'm not 100% sure why.
Okay, well, let's think of it this way. If I were to take an arbitrary element in the complex numbers, could I find a scalar to multiply? So if I take a scalar times 1 plus a scalar times I plus 2, that'll give me the arbitrary a plus bi. See, Eleanor, I was just going to use 1 and I as my basis elements, but you had to go and make it difficult. Aaron?
Well, you could do A minus 2B for your first, and then B for your second.
Let's see, that would give me A minus 2B plus 2B is A for the real component. And negative 2B plus, or hold on. And then just B times I is B for the imaginary component of the output. So yeah, I think this would work. So the set is going to span the complex numbers, and thus this is a basis. You can write any complex number as a linear combination of these two elements. And this is a linearly independent set, which means it is going to form a basis for the vector space of all complex numbers. What I had in mind as basis was 1 and I. A little easier to see how can you take an arbitrary a plus bi and write it as a linear combination of 1 and I. Just take a times 1 plus b times I. But this would also be a basis. Another basis would be 3 minus 17i and pi plus 996i. Yeah, that would be basis. In fact, any set of two linearly independent vectors will be a basis. Because if you remember back in Standard 7, we had rules like, oh, if you have a linearly independent set that has the maximum number of elements in it, then it's automatically going to be a basis. Seems true for an arbitrary vector space. So with that in mind, what's the dimension of the complex numbers? as a real vector space, Henry?
2.
So we could say that the dimension of the complex numbers as a real vector space is going to be 2. Because every basis for the complex numbers has 2 elements. And yes, before someone asks, as a complex vector space, it would be 1-dimensional and have a basis with exactly 1 element in it. But we're not going to worry about that. Any questions or comments? Let's do one more example, and then I'm going to set you all loose to look at a few on your own. How about a set of all polynomials of degree less than or equal to 3? So if you recall, or let's say less than or equal to 2. That's the set of all polynomials of the form ax squared plus bx plus c. What would be an example of a basis for that? Someone who will give me a basis that's not super complicated, please. Liam?
X squared, x, and 1.
Thank you. Yeah, we could say that one example of a basis for this would be, I'm going to go, I like increasing order,
Okay.
but the order in which you write it doesn't matter. I think that's going to be a linearly independent set. 1 is not redundant. X is not redundant because x is not a scalar multiple of 1. No, you can't write x as a scalar. And x squared is not you can't write x squared as a linear combination of x and 1. So this is going to be linearly independent. Is it going to span this set? Well, if I were to give you an arbitrary element in this set, ax squared plus bx plus c, can we find a linear combination of 1, x, and x squared that'll give me this arbitrary ax squared plus bx plus c? No?
Just a times 1 plus b times x plus c times x squared.
Gee, wasn't that a nice basis?
Or the other way around.
Oh my gosh! No, you've tricked me. There, what a nice basis. You just literally peel off the coefficients. It's almost as if this is the nicest possible basis for polynomials of degree less than or equal to 2. It's almost as if we're going to call this the standard basis for this vector space coming soon. It's almost as if this behaves just like the basis 1, 0, 0, 0, 1, 0, and 0, 0, 1 for R3. Stay tuned for standard 9. So this is going to span. So this will give us a basis. So with that in mind, Abriel, what's going to be the dimension of the set of all polynomials of degree less than or equal to 2?
3.
But there's a 2 in it. P less than or equal to 2.
Okay.
It's still 3?
Yeah.
Yeah, because we have to have one for the x term, one for the x squared term, and also one for the constant term. So we can say this is going to tell us right away that the dimension of this vector space as a real vector space is going to be 3. And yes, as a complex vector space, it would also have dimension 3. Any questions, comments, or concerns? Alrighty, in that case, what I would like for you to do is take a minute, look at the next page of the packet. I give you 2 more vector spaces, all polynomials of degree less than or equal to n, and all polynomials in general. go ahead and take a couple minutes, talk to your neighbors, and see for those two vector spaces, can you find a basis and or what the dimension of those two vector spaces would be? Just go ahead and take a minute, talk to your neighbors, and see what you can find. If you want to be cheeky, you can look at the back page as well if you have extra time.
Well, no.
It's just like that, except it goes up to
All polynomials get Zooks.
I mean, it's essentially the same thing.
One question you might ask is, if you were to try and do something similar, is there any finite number of powers of x that would give
Well, they're
you
just X.
everything you need to get all polynomials?
They're not assigned.
But would the dimension be infinity?
No, so what would the dimension
I'm strong. My strength is infinity. Oh yeah, my strength is infinity plus 1. Classic childhood.
I'm gonna say that it is, I'm gonna write it like that, just.
It would not be wrong,
That's good enough for me.
but it would get a frowny face if you put it on quiz.
Answer says, you're not wrong, but, no, stop right there, you said I'm not wrong.
You're wrong. You're not wrong, but I don't like that. I don't like the cut of your jib.
I think that's good. I think it's just like, right?
I do like it.
Is that?
It'd be large.
Yeah, I don't know. It's actually.
Okay, if you think about it, it's
That's
this,
the same
and
thing,
everything
and
else
then
is
it's
not
reversed.
necessarily to
X squared.
So, yeah, I think that's.
Oh, you're right, it's X. Reverse.
Everything goes
There. Right.
So, I mean,
Yeah.
that's not what this is. There, it's just a- Yeah.
What do we have?
Although I guess
Yeah, we have, right? No.
Well, if it was minus 1, that would be right outside, right?
So space.
That one's only three.
What's your question?
Yeah, definitely give these
Yeah, that's what I'm
dots.
saying.
Set the.
That's only three.
Well, for one, if m and n are not equal, the identity matrix won't even be an element in that
I think
set.
it's just the same.
For one, even if you're just looking at, like, say, all 3x3 matrices, I don't think I3 is enough, because linear combinations, those will just literally give you things to the form n000, n000n.
Yeah.
I think you would need more than one matrix to make that work.
I'm not really sure what you're gonna answer.
Now, if we defined addition as multiplication, then you could make that work.
Oh.
Actually, no, I take that back, that still doesn't work. Because that would only give you, yeah, no, that's still won't work.
The road.
For complicated reasons.
Oh, but you know.
We just had
Let's take about another minute and then we'll come back together and talk as a class.
Yeah, you're right, I don't
Yeah.
know.
You could write it like.
Yeah,
We could-
I don't know, I just don't know.
Yeah, no, it would be. There's different sizes, so it's not too great. We just don't be divided as.
Yeah, well,
We want like things that one is as much as counts. But we can call that one.
Oh, wait, no, that's, I'm gonna give a thumbs up.
Yes.
You might not know this, but you're all gonna be on YouTube.
That's just the vector that.
If you just have, only said that it would be,
And
just have a constant, yeah.
So if you had
Like it's all the, just count down until you get to it. So that makes sense as a whole, but I just don't know.
so if you had one
Or-
and then one
So
That'd
like,
be
and
different.
the other way you can't.
and then one.
It starts with dimension.
Right, that's probably.
And those are all linearly independent.
yeah. So that's not the right.
Alrighty, let's come back together and talk about these. So, when we said polynomials of degree less than or equal to 2, polynomials of the form x squared plus bx plus c, we used a basis 1x squared giving us dimension 3. Was anybody able to find an analogous basis for the vector space of all polynomials of degree less than or equal to n? Riley?
1x squared x to n.
Like that? So, I think it's going to be a linearly independent set, because none of these are going to be redundant, because basically you can't take any scalar multiple of an x to get a different power of x showing up. If you take a linear combination of 1 and x, you're never going to get an x squared term. A linear combination of 1x squared is never going to give you an x cubed term, and so on and so forth. I also think this is going to be a spanning set, because any degree n polynomial can be written as a linear combination of these things. So I think it checks out. So Riley, what did you say the dimension of this vector space is then going to be?
N plus 1.
Yeah, because there's n plus 1 of these terms. One for each power of x, as well as for the constant value 1. Meaning any basis for polynomials degree less than or equal to n is going to have n plus 1 vectors in your basis. Any questions or comments about that one? How about this one? Set of all polynomials, where we're not putting any specifications on what the degree is allowed. All right, Ben.
I just put the same thing, but everywhere it says n, you just put infinity.
Everywhere you say it says n, you put infinity.
Yeah, so for the basis, we can have 1, x squared, x to the infinity. So it's gonna be an infinitely large basis,
What is x to the infinity?
infinity.
Is infinity a polynomial?
Ooh.
You wouldn't even need the x to the infinity, but you could just leave it as ...
Just say 1x, x squared, x cubed, x to the fourth, going on forever?
Yeah.
I think so. I hesitate to include something like x to the infinity, because if you look at any single polynomial, none of them are going to have an infinite power of x showing up in them. There is no calc 1 polynomial you could possibly come up with that'll have an x to the infinity polynomial, and if you tried to come up with one, I might have to throw my chalk at you. But yeah, I think we could just say 1x, x squared, x cubed, x to the fourth, x to the fifth, going on forever. Why? Well, it doesn't matter how many of these powers of x we take, none of them are going to be redundant, because each time we go up to a new power of x, there's no linear combination of the terms that come before it that'll that'll give us the new power of x, just like we kind of saw up here. And also, if your basis just consists of literal powers of x, you can also write our basis like this if you want, x to the n, where n is an element of the sets 0, 1, 2, 3, ... That's right, we set within a set. But any polynomial at all, you can always write as a linear combination of some powers of x. And so if we have all possible powers of x that are allowed in polynomials, that would give us a spanning set. So we can have a basis, 1, x, x squared, x cubed, and so on, that does not. What's the dimension then of P? In other words, Kevin, how many elements are in our basis? ...
plus 1.
Plus 1. Yeah, this is going to be an infinite dimensional vector space. And our first example where that sort of thing occurs, where it turns out there's no reason why a basis has to only have a finite number of elements like it does in Rn. You could have a basis that goes on forever and gives you an infinite number of elements. And we would call this then an infinite dimensional vector space, as opposed to a finite dimensional vector space like all the ones we've looked at before this point. So having an infinite dimensional vector space can lead us to a bit of a sticky wicket. Because if we want to say, oh, if every element in P can be written as a linear combination of these terms, Catherine, would you consider this to be an element in P, in a polynomial? 1 plus x minus x squared plus x to the 10th. Ashley, would you consider this to be a polynomial? Negative x plus x squared minus x cubed plus x to the 4th.
Yes.
Yeah, it's a linear combination of basis elements. Eleanor, would you consider this to be a polynomial? X plus 2x squared plus 3x cubed plus 4x to the 4th plus 5x to the 5th plus ...
Yes.
You would? Why?
Because it's a linear combination of the basic.
It's a linear combination of the basis elements?
It can be written as a linear combination of the basis.
But that doesn't look like a polynomial, that looks like a power series to me, or not a power series, that looks like a series to me.
Yes.
So what's up with that?
Can it not be both?
So this gets us into an interesting scenario of when you have an infinite basis, sometimes you need to put a restriction on it. Like all but finite, whenever you take a linear combination, all but finitely many terms have to be have a coefficient of 0 in front of it. Because otherwise, technically, you could say this is in the span because you could write this as a linear combination of basis elements, even if your intuition is kicking and screaming and telling you, Dr. Gerstle, that's not a polynomial, that's a series. Polynomials have to have a finite number of terms in them. Well, if you want polynomials to have a finite number of terms, what happens when you have an infinite basis?
You have to tell it not to be infinite.
You have to tell it not to be infinite. Are you saying this isn't a basis because we can find a finite collection of, can we find a basis with only finitely many terms?
You just put zeros.
For basis elements?
No. If you just multiply 0 by the elements that you don't want.
Okay. So this one's a little bit interesting because when we think of polynomials, like we said, When you have an infinite dimensional vector space, sometimes you want to think about being able to take infinite sums of things. Like for instance, you could think of R infinity as being an infinite dimensional vector space with basis elements 1, 0, 0, 0 going on forever. 0, 1, 0, 0 going on forever. 0, 0, 1, 0 going on forever. How would you write then the Pythagorean sequence? As a linear combination of those basis elements. You would need infinitely many of those basis elements to write that, where all of the coefficients are non-zero. 1 times the first, plus 1 times the second, plus 2 times the third, plus 3 times the fourth, plus 5 times the next one, and so on. Already running out of mental capacity to remember what comes after 4. So sometimes when you're looking at infinite dimensional vector spaces, you have to be careful about, do you want to include infinite sums meaning the sum of infinitely many terms where not all of them are 0 or not. Have a good day, everybody. See you all on Wednesday. So I encourage you to check out the last page of the packet for just kind of for your own practice. But yeah, you can expect on Wednesday's quiz, I'll probably give you an example of something, ask you maybe, is this a subspace? What would be a basis for this? Or is this set of vectors linearly independent and or a spanning set? Would be the sorts of questions I could conceivably ask on a quiz. Good to know. See y'all Wednesday.
Thank you.
Take care.
Dr. Gershel,
What's up, Henry?
could you theoretically express this basis as a Swift notation? So like,
When you say express the basis, what do you mean?
as in like
Like
if you
this.
wanted to limit it, could you say that's your basis?
Well, that's a single thing. That's a single term.
Oh, that's true.
So,
Okay.
I mean, you could write like a base. You could do a basis, and this would be a different basis, but you could do a basis for the polynomials that looks like this.
Oh, I see.
That would give you a different basis, but want something else that works as basis, where every basis element can be written as a sum. So it's basically your basis elements are 1, 1 plus x, 1 plus x plus x squared, 1 plus x squared plus x cubed, and so on. That would give you a different basis.
Okay. It's good.
Think about it.
Thank you.
Take it. What's up?
How do you like write these ones? I think it's like you just try to like have a 1 here and then zeros and then another time you do that, but how would you write that down?
Here's how I wrote it down. I wrote it down with a specific example. How would you write that in an arbitrary case? You could basically say something like, you could write it like that. The answer is not particularly easily. But you could.
What's A? Oh, I see. Yeah. Oh, okay. That's very complicated. Then I guess that's how you do R infinity.
Supposed to be cursive though. Well, R infinity, I would basically say like that.
Oh, okay.
People coming in, pay no attention to our discussion or anything you see written on the board. In fact, you know what? I'm going to erase this right now. So
What's the last one mean?
the The last, what?
The last problem.
Oh, we talked about that on Friday, didn't we? Go back a few pages, not that far back, but a couple pages back. Or set of all differential functions.
Oh, I see. Alright, thank you.
Take care. Nice one.
Minus 1,996.
Ignore this.
It's a complex number.
It is.
I can't ignore complex numbers.
Let me rephrase. Postpone thinking about it for a minute until we come to it in our class. Because I'm trying to avoid spoil. Oh, I forgot to do the video.